Hi everyone, welcome to Shaki. My name is Chandan Saswat, and today we are going to start the machine learning algorithms. So we are starting with the linear regression. So let me tell you that how this course is going to be. So every algorithm we will make two videos. One video will be covering the theoretical part of the algorithms, and another video will have the hands-on session. So this is going to be like this. So today we are starting the theoretical session of linear regression. So let's start. So now we will discuss about the linear regression. So before moving ahead to linear regression, we will discuss about what is regression. So regression is defined as a statistical method that help us to analyze and understand the relationship between two or more variable of interest. Okay, in regression we normally have one dependent variable and one or more independent variable. Here we try to regress the value of dependent variable y with the help of the independent variable, or in other words you can say that you are determining how the value of y changes with respect to the x. Okay, so suppose I have a equation y is equals to mx plus c. Okay, so we just try to determine, or we just try to understand the value of how the value of y changes with respect to x. So x is called as dependent independent variable because this value we supply from outside and we just want to understand the value of y. Okay, so y value is called as dependent variable. Why? Because it is dependent on x value. If x changes, y will also change. Okay, so this is the simplest equation. And what are the types of regression? So first one is linear regression. So linear regression, you have the same equation y is equals to mx plus c. We have a line like this, and this is the intercept which is called at c. And if you have 2 points, you can say that x1 y1 and this one x2 y2. Then m value will be change in y, that is y2 minus y1 divided by x2 minus x1. So this value minus this value. Okay, so this is called as m. So this is your intercept and this is your slope. This is intercept and this is slope. Okay, so this is the simplest equation for linear regression. Now it comes as multiple linear regression. Okay, multiple linear regression. Okay, what is this? So suppose you have equation y is equals to m1 x1 plus m2 x2 plus c. So I'm taking this example only, y is equals to m1 x1 plus m2 x2. So when you provide the value of x and when you provide the value of x2, when you provide the value of x1 as well x2, then you will get the value of y. So this is called as multiple linear regression. Okay, and how the multiple linear regression graph should be. So let's draw it. So we have two independent variables x1 and x2. Okay, so the graph will be 3D. I will not be able to draw it perfectly, but let me try that. If it's x1 and if it's x2 and if it's y, then maybe there will be some plane, okay, which will represent the y value. Okay, because y will be the combination of these two values x1 and x2. So in three-dimensional space the value of y will be a 2D diagram or a plane, two-dimensional plane you can say. Okay, so this is how multiple linear regression we represent. Now the last one is polynomial regression. Okay, so let's say that I have equation y is equals to x cube plus 3x cube plus 2x squared plus x plus c. So we have a degree more than 1, so it is called as a polynomial regression. Okay, the so when you draw then something like this curve, this will not be a straight line. Okay, so that's why it's called as polynomial regression. Okay, so these are the three type of regressions we have. So now let me give you a quick idea what we are going to do in the linear regression. So you already know that linear regression equation. So suppose we have a equation is equal y is equals to mx plus c. So suppose there are some value given for y, 100 values of y and corresponding value of x are given. Okay, 100 samples. Then you will determine m and c in the linear regression. Once you determine this m and c, then any value will be provided in the x. You will be able to say what is the value of y. Suppose after the training phase, when you are doing the model training with this 100 samples, then you get the value of m as 4 and c as 1. Okay, so when I tell you that what is the value of y when x value is 2, then you can say the y value is 9. So this is what in the linear regression we are going to do. So linear regression, how it will be, suppose the car example, this is car model and how many kilometers car ran. Okay, and what is the current price. So you have, suppose car model is 2006 and it's a 50,000 and the price is suppose 1 lakh rupees. Okay, so it's 2008 and this is 40,000 and this is 1,50,000, you can say. Okay, so these kind of samples you will be given. So what is the y here? So we are determining the price of the car. Sorry, so y is car price. Okay, m1, since we have two variables, so x1 is car model plus m2 and how many kilometers car ran plus c, and based on these sample we will try to determine the value of m1, m2 and c, and then whenever you have given these two values you will be able to tell what is the value of car. So this is the whole crux of linear regression, what we are going to do. Okay, so now let's understand the cost function in linear regression. So cost function in linear regression is MSE, mean square error. Okay, the formula is 1 by n sum of I is equals to 1 to n y actual minus y predicted square. Okay, and why this is called mean square error? Because this term you can see that it is a mean and we have square and this is the error term. That's why it is called a mean square error. But how this will help us to achieve the best fit line? So let's see. Suppose this is the line we have. Suppose some data points we have here. Okay, 1, 2, something like this. Okay, so as you know that first time when we draw, the model will draw an arbitrary line. So suppose the equation is y is equals to mx plus c. So model will start with the random value of m and the random value of c. So suppose our model has drawn this line as the first line. Okay, so this is the x value for this point, this is x value for this point, this is and this is. Okay, so these are the values, x values for this point, and these are the y values. Okay, so when model draw this line, then what happens, model is saying that this is my y hat or y predicted value for this x point, but actual point is this. Okay, so what is this? So this is called as error. error made by the model. So the same thing happens here. The line, the model should actually, the line should pass from here, but actually it's going from here and the y value is somewhere here. The same thing is happening here. The predicted values are here, but actual value should be here. Okay. So this is actually a error made by the model. So and this is the equation which tells you how much error the model is making. Okay. And our main goal of linear regression is to minimize this error. Okay. And the second thing is that how to minimize this, how to say to the model that go to this direction so that our error will be less, or go to this direction so that my error will be less. So that is, we do through the gradient descent. Okay. Gradient descent. Okay. So now let's understand first how this MSE helps us. Okay. So now let's deep dive into the MSE and let's see how it helps us to determine the value of M and C. So now I will explain you with M how this will help us to determine the value of M. Okay. You can similarly see for the value C. So the MSE equation is 1 by n sum of I is equals to 1 to n y predicted minus y actual square. Okay. So suppose my line is y is equals to mx. Okay. So the equation is equals to y is equals to 1 to n mxi minus y square. Okay. So now let's do one thing. We will plot m and the error. Okay. MSE error we will plot. So suppose the m value is 1. Okay. I'm just writing m value is 1, but the data we don't have. So let's say that x we have 1 2 3 and 4. Okay. And y we have 2 4 6 and 8. Okay. So I'm just trying to draw with the various values of m. Okay. And we'll see what is the MSE value. So m is equals to, let's start with 0. Okay. M is equals to 1, m is equals to 2, m is equals to 3, and m is equals to 4. Let's see that what are the values we get. Okay. So when you put in the equation here mxi minus y. Okay. So m value we have put as let's say we have 0. Okay. The first value 0, so it will be the y square. So when m is 0, we have simply it's a y square. So 2 square 4, 4 square 16, 6 36 and 64. Okay. And divided by 4, since we have 1 by n, so it will be m is equals to 0, it will be 30. Okay. And when m is equals to 1, so now this m is equals to 1, so m into xi, so 1 into this value 1. Okay. Minus 2, that is 1 square 1. Okay. Then 2 into m is 1, sorry, so 1 into 2, that is 2, 2 minus 4 4, 2 minus 4 is 2, 2 square 4. Okay. Then here 3 3 minus 6 3, 3 into 3 square, that is 9. And similarly here 16 divided by total sum of this and divided by 4, because we have 1 2 3 4 elements, so it will be 7.5. okay. Similarly for m is equals to 2. Okay, so as you put m is equals to 2, so 2 into 1, 2 minus 2, 0. 2 into 2 minus 4, that is 4 minus 4, 0. 3 into 2 minus 6, 6 minus 6, that is 0. And similarly this one will also be 0. Okay, and when you similarly do for m is equals to 3, you'll get 1 4 9 and 16. For m is equals to 4, okay, you will get 4 16 36 and 64. When you do this here, you will get 0. For here you will get 7.5, and for here you will get 30. So when you try to plot this, so x value is 1 2 3 and 4. Sorry, m value is 1 2 3 and 4. And suppose this value is 10, here it is 20, and suppose here it is 30. So when m is 1, m is 0, when m is 0 we have 30, this point. Okay. When m is 1 we have this value 7.5 around here. When m is 2, then error is 0. When 3, it is 7.5. When it is 4, then it is 30. So when you plot this, it will go like this. Okay, so you can see here the error is minimum, or you can say the error is 0 at m is equals to 2. Okay, so this will be determined by our model that, okay, yeah, m is minimum as error is minimum as m is equals to 2, that is coming as 0. By looking into the x and y, so my equation will be y is equals to m, we have determined 2 into x. And by looking into the equation, you can also say that the m value should only be 2. Y is equals to 2 into x. So this is how we determine the value, by using this manual substitution of this m value and the error. So this is the use of this error, MSE error. Okay, but this is we have manually substituted, like m is equals to 0, m is equals to 1 2 3 and 4. Okay, but this will not happen in the machine learning, because if you go to the manual substitution, there will be lot of m values like m1 x1 plus m2 x2, so you have lot of independent variables. Okay, so you cannot do this in the linear regression or in the model building. So how it is done? So there is a technique called gradient descent. Okay, gradient descent. How it works is, suppose you have a value here. Okay, so you are here, m is equals to 0. Okay, so now you know that your uh, global minima, or you can see that error is minimum at here. So wherever your error is minimum, that is called as global minima. Okay, so you can say that you have started from m is equals to 0, and you have to reach at m is equals to 2. So how will you do that? So what machine learning model will do, it will start uh, descending here. Okay, the value of m. And how it works is, there is a something called convergence theorem. Okay, convergence theorem say m is equals to m minus differentiation of error function, okay, into the learning rate. Okay, so how it works is, suppose I have now m value is equals to 4. Okay, in the first iteration, my model is saying that m value is 4. Okay, then when it goes to the second iteration, then the error term minus the learning rate. So 4 minus, suppose this term is coming as 0.5. Okay, this whole term, learning rate into the differentiation of error term MSE, so it is coming as 3.5. so my next value will be, in the second iteration, it will be 3.5 somewhere here. Okay, then next time, suppose it is coming at 3.5, the whole term is coming as uh, 0.4, so my next value is 3.1. Okay, so it will be somewhere here. So you can see how the gradually it is going towards the our global minima, which is 2. Okay, and minimizing the error. Okay, so this is how your gradient descent work. And what is learning rate? Learning rate is, suppose right now we have value is 4. Okay, and suddenly this value, this uh, error term, this error term has a value of 5. Okay, so now the whole thing, m is equals to 4 minus 5, that is m is equals to minus 1. So somewhere it will jump to here. Okay, so it will be like from here to here, here to here, here to here, so the steps are too much. Okay, that's why we have given a learning rate here. So by default the learning rate is 0.1, so that the steps will be smaller, then it will converge. Okay, that's why we add a term learning rate, and this learning rate is provided by the user. Okay, this has to be provided by us. Okay, so now let's deep dive into the gradient descent, and let's look at how the gradient descent works in machine learning models and what happens in every iteration. Okay, so you already know the formula for MSE is 1 by n I is equals to 1 to n y actual minus y predicted square. Okay, sorry. And when you differentiate this, also the convergence theorem explained you m minus d differentiation of this MSE j theta by with respect to m into learning rate. Okay, so let's take learning rate as 0.05. Okay, and differentiation of this, that is differentiation of MSE, it is 2 by n I is equals to 1 to n xi mxi minus y. Okay, so now let's try to understand. So suppose I have a data x and y. Okay, x values are 1, 2, 3 and 4. Y values are 3, 6, 9 and 16. So I have taken a simplest equation, that is y is equals to mx. Okay, and as you can see the m value is 3. For every value of x there is a 3 times value of y, but we are trying to determine this value through the machine learning. Okay, so as the equation here is, this is my differentiation of this. So if x value is this, y value is this, then what is the value of mx? In the equation we have this mxi, so we will sum later. So mx we will determine, and then we will determine xi, actually x mx minus y for every value. Okay, So mx will be 5. Let's start with m is equals to 5. Okay, so m will be 5, then m into x. So m into x, m is 5 into 2 10, 5 into 3 15, 5 into 4 20, and then mx minus y, mx minus y 2, 2 into 1 2, 10 minus 6 4, 4 into 2 8. Okay, similarly this is 18 and this is 32. Now what is the sum of this? So sum of this is 60. Okay, so this whole term is giving me 60 into, you can see here 2 by n. So how many it will be 2, and how many total samples are there? So 1 2 3 4, so it is 4, so it will come as 30. Okay, so now what the convergence theorem says, m is equals to m minus differentiation of this, differentiation of MSE and learning rate. Okay, so now my m is 5 minus 0.05, the learning rate I have taken 0.05 into 30. Okay, then 5 minus 1.5, 3.5. So now my new m value is 3.5. So this is iteration 1, what the machine learning model is doing. Okay, so now let's go to the iteration 2. Okay, iteration 2. So my new value of m is 3.5. Okay, so let's draw again the x value, y value. So x value was 1 2 3 and 4. Okay, and this value was 3 6 9 and 16. Now mx value, so what was the mx value? The 3.5 into 1, that is 3.5, 3.5 into 2, 3.5 into 2 7, and this value similarly 10.5, the third value, and the fourth value is 14. Now xi, not xi, x mx minus y. So 3.5 minus 3 into 1, 0.5, and similarly all these values 2, 4.5 and 8. When you do this sum it will come as 15. So 15 into 2 divided by number of samples, that is 7.5. Okay, so now again the convergence theorem, m is equals to 3.5, the m value, minus the learning rate 0.05 into the differentiation of this, that is 7.5. So it will come as 3.125. Okay, so you can see that earlier we were into 3.5, now we are near to 3. Okay, so now let's go to iteration 3. Okay, so this is the x value, y value, 1 2 3 4 3 6 9 and 16. Okay, mx and x, mx minus y. So now my new m value is 3.125. Okay, 3.125. So mxi 3.125 into 1, that is 3.125. This value is 6.25, this value is 9.375, and this value is 12.5 and this value is 0.125. This value will be 0.5, this value 1.125, and this value will be 2.0. So when you add this, it will come when you add this value and into 2 by 4, it will come 1.875. okay, so now m is equals to 3.125, that is my old value, minus 0.05 into 1.875. When you do this, you will get 3.03125. So you can see after 3 iterations we are very near to 3. okay, because we already know we have given a value y is equals to 3x. okay, and we are the m value after the third iteration we are able to reach near the 3. okay, from the gradient descent and convergence theorem. okay, well, let's see one more iteration. okay, so iteration 4, x value, y value, mx, and the same way it works in the machine learning model. okay, x minus y. So 1 2 3 and 4, 3 6 9 and 16. mx value 3.03125. this value will be 6.0625, 9.09375. this value will be 12.125, and when you do this you will get 0.03125, 0.1250. the third value will be 28125, and this will be 0.5. so when you add this and divide it by 2, you will get 46875. so now it will update it as the new m is equals to 3.03125 minus 0.0234, and it will give you 3.0078125. so you can see as the iteration is increasing, we are going closer and closer to 3. okay, same thing happens in the machine learning model. When the iteration goes higher, we get our best value of m, and when it stops, so when it sees that there is no more changes into the value of m, then it stops. okay, so now we are going to see what are the 4 assumptions of linear regression. The first one is linearity. okay, so the mean of the data is a linear function of independent variables. okay, for each unit increase in the independent variable, the mean of the dependent variable increases by the same amount regardless of the value of independent variable. So suppose I have this one, this is my independent variable, or you can say my x, and this is my dependent variable, you can say y, and suppose this is my regression line, and these are some points. So it's saying that the rate of change of y, the here, should be the rate of change of y here. okay, in the unit increase if we are going, then the rate of change of y should be here, it should be equals to this. okay, so this is the first assumptions of linear regression. So the second assumption is normality. okay, normality, so it is related to the residuals. okay, so residuals I have already explained. Suppose this is your independent variable and this is your dependent variable, this is y and this is x. So and this is my regression line, and suppose these two are my actual points. So the actual point versus the predicted point, this is my predicted point and this is my actual point. So these are called the error made are called residuals. So residuals to be normally distributed, okay, the residuals should be the normally distributed, and regression line is fitted to the data such that the mean of the residuals is 0. So suppose if I have another points, okay, here, so the mean of all these residuals should be 0, okay. So this is my second assumptions, okay. The residuals should be normally distributed and the mean of residuals should be 0. And if this is not coming, then you have to transform your data, okay, transform the data, and you can check this by using the histogram, and you can look it is looking like a normal distribution or not, okay. So this is the second assumption of linear regression. So now we are going to see the third assumption of linear regression, which is equal variance, okay, equal variance. So what does it say is, linear regression assumes that the variance of the residuals is same regardless of the value of the dependent or independent variable. The issue of homoscedasticity, okay, if variance of the residuals varies, they are said to be heteroscedastic. So suppose I have this x, this is y, I mean my dependent variable, this is my independent variable, and this is my regression line. Suppose some points are here and some points are here. So you can clearly see the variance what we are seeing here is not equal to the variance what we are seeing here. So this is called your heteroscedasticity, okay, because this variance is very large and this variance is very less. So how to deal with it? So to check if your data is heteroscedastic or homoscedastic, you have to run this Goldfeld quant test, and if you find your data is heteroscedastic, then go for box cost transformation. So box cost transformation formula is y lambda is equals to y lambda minus 1 divided by lambda, where lambda is not is equals to 0, and log y if lambda is equals to 0. So what it will do is, it will just try to bring this variation or the variance closer to the regression line, or it will try to minimize these variance, okay. So box cost transformation, what this will do, okay. So this was the third assumption of linear regression. Now what is the fourth and the last assumption of linear regression? So that is independence, okay. So suppose my formula is y equals to m1x plus m2x m3x plus c, okay. So what it says is, these independent values should be independent of each other, okay. That means any changes in this should not affect any changes on this or this. Why is it so? Because this is called the dependent feature or dependent value, and we change this value and note this value, okay. Then again, for some values we'll change this one and we'll note down this one, okay. Change in independent variable, what is the change in the dependent variable? But if these variables are correlated, then what will happen? You'll change this one, this will change, but this value will also change. So we will not get the correct value of y. That's why it should be, the features should be are not correlated to each other. Okay, so there are two things that we check: correlation, and second one is multicollinearity. So correlation, I have already explained you a lot about the statistics video. So if you have not watched, please watch that statistics video where I have explained the Pearson correlation for the continuous value and chi-square for categorical value, and we will implement these two in linear regression whenever whenever we have to check the independence of variable. So this is mandatory. Multicollinearity is the linear relationship between the features, two or more features. Okay, so how to check? So there is something called VIF, that is variance inflation factor. The formula is 1 by 1 minus r square. R is actually the coefficient of determination, which I will explain later. So r square value ranges from 0 to 1. Okay, and how to calculate this? So you can say if you have a greater VIF, then greater correlation. Okay, so suppose you have 4 or 5 features, and I'm just trying to get what is the VIF for all the features. And suppose I have here feature 1, feature 2, feature 3, feature 4, and feature 5. This value is 2.02, this value is 12.01, this is something 14.03, 3.01, 4.03. So these value, you can see the values of VIF is more for these two values, feature 2 and feature 3. So, and high value of VIF, so generally we consider if the value is greater than 5, then we consider it a high value of VIF, and there will be, and we assume that there will be a correlation between these two. Okay, so what we do is we drop one of the feature with the high VIF, and then we will run this again. Okay, and then we draw this VIF, and if we find that the values are, some values are still very high, then we will try to drop another column, and then we will run again this VIF, and then we will do until the values are VIF values are normalized. I mean the less than 5, if all values are coming, then it's okay. So this is how we reduce the collinearity here, the VIF. So now we are going to see what are the regularization technique in machine learning. So let me tell you first why we use regularization. So by using this, we can avoid overfitting in our model. Okay, second one is like it reduces variance without increasing the bias. Okay, so in the machine learning also and in the deep learning also, this regularization we are going to use a lot. There are different techniques for regularization. So in linear regression we have lasso and we have ridge. Lasso is called as L1 and ridge is called as L2. Okay, so what is ridge and what is lasso? So ridge is we have RSS is equals to sum of I is equals to 1 to n y actual minus y predicted square plus, now we are adding a penalizing term. Okay, that is lambda. Here something j is equals to 1 to n, and this is beta j square. So You can see here this is the normal term which we use for getting the errors, and this term we are just adding to penalize it whenever there is a coefficients dominating into the model, then we are just penalizing that. That means if I have this y is equals to m1 x1 plus m2 x2 plus dot dot plus this lambda sum of bj square. So you can see here if some coefficients like m1, this is coming as 10,000 and this is coming as 2. So we are just by penalizing this, we are just ensuring that every coefficient will participate in the model. Okay, it's not just like one coefficient which is dominating into the model. Okay, we are just because this x1 value depends on the value of m1. Okay, the what is the importance of this into the model, it depends on this m1 value. The importance of this x2 depends on what is the value of m. If this is the minus value, then it is impacting negatively to the model. If this value is 0.00001, then there is no importance of this feature, correct? So by penalizing this by coefficient square, we are ensuring that every feature is participating, or every coefficient, we are not letting anyone to dominate into the model. Okay, so this is sorry, so this is the rich way, and this is also called as L2. Okay, now the second one is lasso. So lasso is also called as feature selector. Okay, because it makes some of the features 0. Okay, that's why we call it as feature selection technique. So the equation of lasso is sum of I is equals to 1 to n y actual minus y predicted square plus lambda sum of absolute value of coefficients. Okay, you can say j is equals to 1 to something p, and this is bj. So this is the lasso equation, and you can see that we are penalizing with the absolute value of the sum of absolute value of the coefficients. Okay, so and you can always see that we are penalizing, and we have a term here that is lambda. Okay, so here also we have lambda. So when lambda is equals to 0, it will be a normal MSE equation, MSE or RSS equation. Okay, but when we are taking lambda too much, I mean lambda is greater, then what will happen, it will penalize more the coefficients. Okay, and when lambda is less, then it will penalizes less the coefficients. Okay, and lasso is also considered as the feature selection technique. Why, we'll see now. Okay, and by the mean feature selection, that means suppose I have a equation called y is equals to m1 x1 plus m2 x2 plus m3 x3 plus dot 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 plus c. So when you are running lasso, then what it will do, it will make some of the coefficients as 0. So you can see that there is no importance of this x1, it will make this coefficients at 0. So there will be no importance for this, then our equation will be m2 x2 plus dot 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 plus c. Okay, so these coefficients will be 0, so there will be no impact of these features on the model building. Okay, so now we'll see how this lasso used as a selection technique, feature selector. Okay, so this is the diagram which I got from internet, and suppose there are only two coefficients we have, beta 1 and beta 2, and this is the two-dimension plot which we have plotted. So this side is a beta 1 and this side it is beta 2. So we know that the sum of absolute value is our lasso regression, and suppose this is the value t, some random value we have taken, and we are just drawing this graph. So it will be like a diamond shape. Okay, it will be like a diamond shape, and we know that in the lasso we penalizes with the sum of coefficient square, and this is some a random value. Okay, so less than the value c, so that the all the inner points we can consider. So this will be our beta 1 square plus beta 2 square less than equals to c, and this is some plot, the value of b1 beta 1 plus absolute value of beta 2 less than equals to t, this graph, and this is our equation for cost function. Okay, so cost function is how it will be plotted is like a elliptical graph. Okay, this is like this. So when these touches here, then that time some of the coefficients become 0 every time it touches to the corners of this. Okay, then it will make some of the coefficients as 0. Okay, that's why our lasso is considered as feature selector, and it doesn't happen here. Okay, because it doesn't have a sharp shape or the sharp edges, that's why it won't happen here. It happens in the lasso, that's why sorry, lasso is considered as a feature selector. Okay, so now we are going to discuss the evaluation metrics for a linear regression model. Okay, so what are the metrics available? So suppose you have built a model. Now how do you know the model which you made is correct or the good model, and what is the accuracy it is giving and all? So how will we determine this? So there are some evaluation metrics we have. The first one is, I have already explained, MSE, RMSE. RMSE. MSE is mean square error, RMSE is root mean square error. So MSE formula, as we already know, 1 by n sum of I is equals to 1 to n y actual minus y predicted square. So this is MSE, and when you put a square root here, then it becomes RMSE, root means square error. Okay, so lower these values are, better your model is. Okay, so our main goal of building the model is to uh, decrease or to reduce this value. Okay, as much as we can reduce, we reduce this value. Okay, and you can see we have a square here. Okay, so suppose in the regression line you have 1 point here and 1 point here. So suppose this point is 2 and this point is 4. So since we have a square here, okay, so if we have more distance or the more residual, then the penalization is more here, because we are penalizing with the square value. We are making it square. So the for incorrect value, or when the residual is more, our we will penalize with a square uh, to the value. Okay, now the second one is MAE, mean absolute error. Mean absolute error. Okay, so the formula is, this is 1 by n sum of I is equals to 1 to n y actual minus y predicted, the absolute value of it. Sorry. So this is actually the direct representation of your error. So we don't have any square here. So this is the value. If I have a point here, so it is taking just this value, not square, not anything. Okay, so it applies here also. The lesser value will be uh, good for the model. Okay, the third one and the most important one is R square and adjusted R square. Okay, R square and adjusted R square. So R square is variation explained by the model, variation explained by the model divided by total variance, and the formula 1 minus RSS divided by TSS. RSS is sum of square of residuals, okay, this one, and TSS is total sum of square. So it will give you the R square. So R square is basically, if you have so it is the coefficient of determination, as we have seen. So R value, R square value generally 0 to 1, or you can say that it value ranges from 0 to 100%. So how it impacts in the regression line is, suppose this is the regression line and your points are scattered like this, okay, like this. We have some another one we have, okay, another we have, and we have a line here, and this time the points are closer to the regression line, okay. So you can see that it is sparse to the regression line. So you can say here that your R square will be around 20% or 0.2 the value, and it is closer to the regression line. So you can say here it is around 80% or 0.8 your R square value, okay. So you can assume that if R square is more, the better your model is, okay, and if R square is less, the your model needs to be improved, okay. And R square, if R square is coming at 0.8, that means your model is able to explain 80% of your data, okay. So that's how we interpret this R square value. If it is coming as 0.9, then your model is able to explain the 90% of your data, okay. So this is R square. Similarly, there is something called adjusted R square. Adjusted R square. So adjusted R square is, suppose there is an equation called m1 x1 plus m2 x2 plus c, okay, and your R square value is coming 0.8, suppose, okay. Then what I did, I added another variable m3 x3, okay. So your R square value increased to 0.82, okay. And when I calculated this adjusted R square value, I got adjusted R square value as 0.7, okay. So earlier when it was 0.8, suppose my R square value, adjusted R square value was 0.7. Now I added one more feature, m3 x3. After adding this, what happened, my adjusted R square value dropped to 0.6, okay. So what adjusted R square says is, it says that if you are adding any new feature to the model, okay, so if model is able to explain this feature, okay, if model is able to explain this feature, then your adjusted R square will increase. If this feature is model is not able to explain this feature, then your adjusted R square score will go down, okay. So this feature should be important to the model, and model should able to understand this feature, then only adjusted R square will increase, okay. And adjusted R square will always be less than r square. Okay, because whatever value you will add, r square will increase, but it will not happen with adjusted r square, because if you add the junk value, this value will go down. Okay, and this value ranges from 0 to 1, and the adjusted r square value can be negative. Okay, so sometimes in the interview they ask what r2 value, adjusted r square value can be negative or not. Okay, so remember this. Yeah, so these are the 4 evaluation metrics we have. So this is the end of theoretical part of linear regression. So if anything else will be there, I will be explaining it in the practical part. So next session or the next video which I'll be making, I'll make the hands-on session, or I'll show you with some example, real-time example, how we build the model of linear regression. Yeah, thank you.